Hello, good morning from Brussels. I want to do a very short video because I still get remarks on why I don't say anything about gravity in my papers, and the reason is quite simple for me. Gravity is sort of a solved problem, I would say, and Einstein solved it just like he solved many other problems, and he brings it back to the curvature of space, which for me is a very natural thing in the sense that Cartesian space is infinite. If we think about the universe in terms that we can understand philosophically, logically, ontologically, infinity is kind of weird. We think the universe started somewhere, and so it should probably also end somewhere. The border of our universe may be moving further and further away from us, and like Big Bang theories. But yeah, it's just non-Cartesian space, curvature of space-time. So it's rooted in special relativity theory, but then applied to a whole a different set of issues. I want to show here because that's something I also get. It's like okay, gravity and electromagnetism. How can we relate the universal gravitational constant to charge and Planck's quantum of action perhaps? And for me, it's quite easy. My models and my worldview of elementary particles are mass without mass models. I illustrate that here. So, for instance, for an electron, the energy of an electron, and so it's equivalent mass, I would say, instead of usually we say the equivalent energy of a mass, but I say the equivalent mass of an electron, in the sense that mass then becomes a what it is in kinematics, inertia to a change in the state of motion of that electron. It is inertia to a change in the state of motion of an energy packet, I would say, for an electron and a proton. And the energy comes from an oscillation, a force acts on a charge. And so I think about a naked charge that is photon-like in the sense that it has no mass of its own, and so it has to move at the velocity of light. And so, yeah, I think about an electron as an oscillation in two dimensions, two linear oscillations, and this oscillation obeys the Planck-Einstein relation here. Its energy, the energy in the oscillation is the reduced Planck constant, the quantum of physical action times the frequency of the oscillation, and then we have the orbital velocity formula. C will be the radius of that two-dimensional oscillation, something that goes up and down and sideways, goes around in a circle, times the same frequency, really physical orbital frequency of that naked charge. Now we get the Compton radius of an electron, and that's it. So it's a mass without mass model, and in that sense, I like to think about gravity as the force. It's pseudoforce, as said in a non-Cartesian view of what the geometry of the universe is. It becomes a force between energies, and so when you want to relate it, actually that's very easy, because people say you don't think about that, but I do actually. We can here, right? Okay, the gravitational force, and I said there's no gravitational charge, but force or pseudoforce. Let's see its strength as compared to the Coulomb force between the static the force between two charges. We know that's written like this: the electric constant times the product of the two charges divided, it falls off with the square of the distance between the charges, which is like how energy densities work. The gravitational force is this universal big G constant times the masses, but I said I want to write that more in terms of because masses with the revision of the 2009 system of SI units, it's energy that is really the fundamental thing to think about, because then we can also think about the energy in fields, in electromagnetic fields, and they will also attract each other. So it's a force of attraction between energies that are clearly located somewhere in space at some point in time. If we rewrite that, we have G read here out. Here we have the inverse of the Coulomb constant. A mass is energy divided by c squared. So I have 2 times c squared. I have c to the power 4. And then I still have my product of the charges here. So what you can clearly see already is that the gravitational force, it's different between 2 electrons or between 2 protons, because their energies are different. And so but the charges, unit charges, are the same. So it's this Q over E ratio that determines that this quotient here. And I said it will be different for, say, an electron or a proton or a composite I put here non-neutral particle, because of course the Coulomb force will be 0 for neutral particles. So we can't do much with that. So we should consider charged particles, and if we want to write sort of G, or attempt to write the universal constant of gravitation in terms of charge and stuff, we should think about elementary particles only. So if we do that, we can consider an electron and a proton. The mass, or the equivalent energy of a positron and an electron, will be the same. The unit charge is their charge with an opposite sign. And this is already something interesting when you write it out. You see that here we will have a minus sign, minus the electron charge squared. And you think like, oh, we're left with a positive ratio, and now we have this minus sign. What do we do with it? This formula, I said, makes only sense if we think as one of the 2 energies being a negative quantity as well. And you will say, like, how do you justify that? That makes sense if we consider the spin of the naked charge inside of an electron and a positron, which will be opposite for the same magnetic field. So I'm gonna let you think about that, but when you think about energy as a force over some distance, well, the distance can be in one direction or measured in the other direction, and that's why this minus sign appears up. So let us write what we do here. Quite simply, this ratio as 2 times, the square of the electron energy divided by the square of the unit charge. We can do the same then for, a proton and a positron. Sorry, an anti-proton, positive, negative charge, and then we will have in here the proton energy squared. So the Coulomb force will be the same, and the gravitational force between a proton and antiproton is clearly different than that an electron and a positron, because the mass energy is very different, and we can explain that. In my mass without mass model, I derived the radius of a proton, and it's much smaller for 2 reasons. The energy is it's a 3-dimensional oscillation of charge, and that's a funny thing which I'm not going to delve into. A positive charge inside of a proton, or the positive charge inside of a positron, the antimatter counterpart of an electron, appears to be different. So the naked charge has no, I often said that, no real properties except of its charge, but we do have an electron charge, and we do have an antiproton charge in two different negative charges, because they don't annihilate each other when you combine them. Any case, I'm off track already, and that was not the idea. Let me just clean up my sheet. Yes. Yeah, as I said, I can. If you give me sort of a standard your distribution of matter and energy, are you talking about how many electrons, how many protons? Are you talking about an atom? Are you including the fields? The My models, mass without mass models assume there's kinetic energy, but also the energy in the field that this rotating charge generates. Yeah, if you give me a standard distribution of what you think of in terms of the structure, the distribution of charge, how where they go, the fields, then I can give you indeed an relationship between the gravitational constant and the constants that appear in electromagnetic theory, the unit charge, Planck's quantum of action, speed of light, etc. But yeah, more than that we cannot really do. So the interesting thing is to show what I just said is that we develop this ratio between the gravitational force between an electron and a positron, and between a proton and an antiproton, and we arrive at the that ratio should be equal to the squared electron energy and the squared proton energy. So there's no fixed relationship. There's just one for two very different types of elementary particles, electron versus proton. So we can translate it back into mass factors, but I said I like to think in terms of energy. And the interesting thing I want to note, and I'm almost done with my lecture, you will see it's going to go very, very fast, is that the electric constant, you know that since the also 2019 revision, well, actually earlier, the fine structure constant was defined in terms of the Coulomb constant, unit charge, and H and C like this. The fine structure constant is equal to the squared unit charge divided, multiplied by the Coulomb constant, and then divided by H bar times C. So this is very interesting, where we can, the ratio of the gravitational force as compared to the Coulomb force, we can do a substitution here and write 4p 4p times the electric constant as alpha times hc, and let me see here how I do this. Yeah, the c square. I might have forgotten that one. G. Yeah. You see, I do make mistakes. We have c to the fifth here. 4p E is q e squared divided by alpha hc, and we still have that 1 over c4 here. Interesting. So here we would have c to the power 5. But it's an interesting formula. I see it's always good to try to explain something on a whiteboard or in a video, because you discover mistakes in the formula. So we have this very interesting formula for the ratio between the gravitational force and the Coulomb force, that it is the universal gravitational constant times the square of the energy, with the energy that can be the energy of an electron or a proton. I said we need to think in terms of specifics, gravitational force between which particles, divided by alpha times h bar c to the power 5. Quite remarkable here. Do check it out numerically, because it's an interesting one. Makes me feel of the factor 5 that you have in how the dipole field drops off, but that's something else. Clean up the sheet again. Except for that factor 5. So yeah, let's do some thinking about that formula then, where I said that the ratio of the gravitational force and the Coulomb force is g times the square of the electron squared times okay, here I'm really not in shape here. Should then put that alpha H C5 factor. Um, So it's a force, it acts on mass or equivalent energy. And I said, if G would be zero, this is then we would live in a Cartesian infinite space. For me, universe is closed, and it means that we have to bring this down to the local level, and that means that effectively any concentration of energy or matter on the equivalent mass of the energy, be it as matter particles, electrons, protons, or plain electromagnetic fields, um, will attract each other and will create sort of its own non-Cartesian space around it, the curvature. So it is a force, but a pseudo force. And why do I say that? Well, if you look at the Coulomb force, that's a force where we can clearly say, well, it acts on a charge, the electric charge. And we do not have the equivalent of a gravitational charge. I said energy and the equivalent mass of an energy arises actually because we have this special electromagnetic force that acts on a charge and in matter particles like elementary particles like protons and electrons, makes it move around and creates therefore mass really in a kinematic sense, really the inertia to change in the state of motion of that oscillation. So we do not have a gravitational charge, and that's where I'm saying, I'm perfectly fine and comfortable with Einstein's interpretation of gravitation as a pseudo force which arises from a certain curvature of our universe of space itself. So there I want to then go, because I get sort of like, well, look at my model. I have here a hypothetical quantum, and then I'll already go like a quantum of what? A quantum of energy, quantum of linear or angular momentum, or are you talking really about, well, angular momentum? That's H itself, the quantum of physical action. This is the unit of angular momentum. So then they load all kinds of properties onto their quantum particle, and they say, well, look, this is maybe the graviton that we are looking for. I'm not looking for a graviton. I think a graviton is a hypothetical particle associated with, it's not associated with the real force, it's a pseudo force. So, of course, you will say, well, but there are gravitational waves. Yes, when the distribution of matter energy in the universe changes, the rest of the universe will be aware of that, I would say, but that's a wrong term. A change in the distribution of matter and energy somewhere in the universe must ripple through space indeed, and that gives us the concept indeed of a gravitational wave, which has been, as you know, by LIGO Lab and whatever, experimentally confirmed. There are gravitational waves that change, two galaxies, a matter and antimatter galaxy, that annihilate each other, and you've got some kind of big bang there, and then we can discuss whether charge gets destroyed, but it's clear that the motion of the charge is there, and the antimatter counterparts, it becomes a whole different thing, and energy gets converted into electromagnetic energy, linear, angular. We have a different distribution of matter energy on that place where these two galaxies, the matter and the antimatter galaxy, disappeared in a big bang. And so the gravitational wave exists. We can measure that, and that has been measured. And so, of course, everybody thinks now, oh, well, it's a gravitational wave. So we have an analogy with electromagnetic waves, and then we know electromagnetic waves, they carry energy, and that energy is carried by photons and the quanta of light. And so that gives, but it's an anthropocentric or energy. There must be a photon-like carrier of the energy in that gravitational wave. But that's where I'm asking, we have gravitational waves. Yes, sure. But do they carry energy? I don't think so. That's what I write here. They're really just manifestations of that changed distribution of matter and energy. And as such, it's a signal that doesn't carry energy. They change gravitational waves as they move through space. They change the non-Cartesian geometry of the universe, but unlike electromagnetic waves, there is no reason to assume that they consist of quanta of energy or that they carry angular momentum or other things. So I don't believe in gravitons, and that's also why I don't believe that any grand unification theory. I think my theory is fairly unified. The idea that somehow we should include gravity as a real force and then explain gravitons. Well, gravitons, as said, I don't see any reason why we should suppose that gravitational waves carry energy that is packed into these hypothetical particles that we refer to as gravitons, and that's it. And so that's where I just want to be quick. Where if I get papers asking me to review this or that, I believe there's the SI revision of physical units, Planck's quantum of action, unit charge, speed of light. That's really all of physics, and it has it's a model that is complete. I talked about my dark matter, dark energy hypothesis in the last video, which probably is a crazy theory, but it explains or exploits, I would say, an asymmetry that you have there. And so why not consider it? But sort of again, grand unification theories, or people who ask me like, okay, gravitation, what's the explanation of it? Well, it is what it is. What Einstein said, what it is, and I said for me, that's not a logical hypothesis that we live in a non-Cartesian space. I said if G would be 0, we would live in a Cartesian and infinite space, and that's kind of for me not very natural to think of if you have a religious worldview and believe God is infinite and whatever. For me, just like something that has no size, physical dimension whatsoever. The naked charge inside of an electron or proton has a size, explains the anomaly in the magnetic moment. For me, logically, something that has no size, no physical dimension whatsoever, that's something that has no reality. It doesn't exist. And so for me, that hypothesis is, or that statement, logical philosophical statement, is natural, and statement that we live in a non-Cartesian space, which is finite, for me makes as much sense. We need these mathematical idealizations, the idea of God, you may call it in math, to work with integrals and do differentiation and these kind of things. But we should also recognize that reality is discrete, is quantized, and so that explains it all. I'm gonna stop here because I do feel I'm a bit rambling, and but it's a note I wanted to make. As said, rather than writing it out for or as a footnote in my papers, it's probably good that I have a little video here and two slides or whatever you want to call it that lay that out. So yeah, 20 minutes short video. Have a nice day. I'm going on the bike, and this really might have been my farewell a little bit to my thinking on what physics is all about, and especially around all the nonsensical or mystical or guru-like explanations and questions you'll find in popular science books. So that's it. I thank you very much, and I wish you a very nice day.